Bonjour, je suis Manaï Bilal, un ingénieur calcul qui a travaillé chez Airbus Atlantique Tunisie pour 7 ans. J'en ai fait mes études universitaires chez l'ESAT, École supérieure de l'aéronautique et technologie en Tunisie, pour le diplôme d'ingénieur aéronautique. Et de suite, j'en ai fait un master en Aerospace Manufacturing Engineering chez Shenyang Aerospace University. Alors, je suis spécialisé dans le domaine de calcul, pour justifier les non-conformités, sur les aéronefs. J'en ai travaillé sur le programme ATR, Bombardier, l'A220. J'en ai touché le cockpit, le fuselage, les ailes de l'avion. Alors, par ce qui suit, j'en ai voulu vous parler de mon métier et aussi faire un petit résumé du livre Airframe Stress Analysis and Sizing de Monsieur Nio. Alors, on va commencer par une introduction. Je vais parler en anglais parce que la plupart du travail maintenant c'est fait en anglais, que ce soit chez Airbus, chez Boeing, les grandes maisons de l'aéronautique. Même pour les autres industries, je n'ai pas de grandes idées pour les autres industries, mais l'anglais c'est un peu dominant côté science, côté langage technique. Alors, the stress engineer is a rich job, while some work in justification phase, and in treatment of concessions with calculations, simulations, and FEM jobs. It's a rich job that applies to different fields like aircrafts, cars, trucks, most vehicles, boats, ships, engines, some types of drones, and even for some toys industries. What you need to know is that you should be aware, as in the preface of the book Airframe, Stress Analysis and Sizing by Mr. Neo, that AI would be the tool like the computer, and that you need the knowledge to manipulate it and work with it. But essentially you have to have the knowledge and the understanding of the basics and fundamentals of your work, the stress engineering analysis science, the physics, mechanics, mathematical formulations and equations. No aircraft engineer can expect to go far in advanced drafting, layout work and design without working knowledge of stress analysis. An engineer is not a robot or a machine. Nowadays, the involvement of AI, the artificial intelligence, the involvement of AI is not an obstacle as much as enhanceable. Many engineers in different fields would replace the hard work of analysis by check and validation work. So an engineer who only knows how to do inputs to computer analysis may not know whether or not the output is correct, the garbage in and the garbage out process. Pardonnez-moi, j'en ai oublié un truc. J'en ai dit justifier les non-conformités. C'est plutôt justifier les solutions du non-conformité. C'était un mistake dans le début. Next, Chapter.1 General Overview. So, knowledge of structural design methods and an understanding of the load paths are essential to advancement in nearly all phases of airframe engineering. So what you should know is that in the design office, while in the certification phase, in the sizing scenario, or even while in the production or justification of concession solutions, you need to know that there is a cycle inside of the design office. Whether to optimize the structure or even for any modifications or any new aircraft, or to justify a solution, there's a cycle where there's a designer and there's a stress engineer who work on that, at least aerodynamics, like aerodynamics specialists, material specialists. That's necessary sometimes to interfere in the cycle. So any aircraft in the production phase, before to go to the production or while the production, and we have a concession that we need to justify the solution of reparation to repair the non-conformity. There is a cycle, and that's done by a quality engineer to report the status of non-conformity, for example, and a designer who gonna give the solution. Then there is a stress engineer who gonna justify that solution is accurate, that solution would assurate the navigability of the airplane, of the aircraft. So we're gonna be focusing about the stress engineers that gonna justify at the certification phase the structure, or justify the solutions for the concessions. So the primary function of the structure is to transmit forces or loads. From the structural engineer's point of view, the objective is to do with the minimum possible weight and minimal cost. In the general sense, the optimum structure is one that does the best overall job of minimizing the undesirable qualities: weight, cost, repair, maintenance. Of course, we should know that weight is an undesirable quality. I mean, increased weight, that means more material cost. So, and it may give increased fuel economy while the airplane cruising. And in the opposite hand, a thin structure needs to have a positive security margins for the backlinks. And we're gonna see next in the next slides what's the notion of backlink. What is it physically? What is it mathematically? What's backlink? What happens to a structure? And we're gonna see what's the phenomenon of backlink. So for structural engineering purposes, this optimum structural design can be done most conventionally by using the structural index, because the structural index is most useful in determining what constructions and or material to fit a particular loading. The structural index can be used to quickly size structures, select the most efficient material, identify the lightest type of construction. For the structural index, for more details, you may refer to the book at page 7 and 8 and find more information. So we're going to talk about mechanical solicitations like compression, tension, bending, torsion, shear, as described in the picture. And also there's the phenomena of inter-rivet buckling or inter-joint buckling. Like you see, we are applying a load with the hands in the right hand picture. There's two hands applying loads on the paper, and you see the phenomena of inter-rivet or inter-joint buckling, or inter-rivet, inter-joints, like whether you have rivets, you have if you have bolts, inter-bolts, or inter-joints buckling. There's like you can see applying loads. You applying loads with the hands. You can see the buckling. That's the phenomena of buckling as described in the picture at the right hand. Also, as you see in the picture, the compression load plus shear load, that's buckling. That's the phenomena of buckling. And as you see the phenomena of buckling at the real picture, that's the buckling phenomena. So applying loading on a section, that's stress. So we're gonna be talking about stress engineering, and the definition of stress, mathematical definition, is the load per section. You just divide the load on the section, you get the stress. And if you have an allowable stress or load, and you divide it on the applied stress or load, you get the security margin. So security margin is equal to the allowable on the applied, to the allowable divided by the applied. So the allowable load, we can get it by we have the data. We need to have the data. A company in the industry, you get the data of the allowable of the materials that they are used in the fabrication and the production. So, and how you can get this allowable is it's simple. You just need specimen, and you just you need to have specimen, and you apply the mechanical solicitation like tension, shear, and you get the allowables. We're gonna see a video of a specimen and how we get the allowables. Alors, on applique le loading comme vu dans les vidéos des éprouvettes. Et on applique le loading et de suite on trouve la courbe du contrainte par rapport à la déformation. On peut voir le domaine élastique, le domaine linéaire, c'est le domaine élastique, et après on vu le non linéaire du domaine plastique jusqu'aux ruptures du matériau.
Have you ever been afraid of your plane wings snapping during turbulence?
Like for static verification of security margins, in order to guarantee the navigability of airplane, we check the fatigue, while getting its allowables is by testing the aircraft, its parts or its assemblies to a cyclic loading, like we can see in the video.
Have you ever been afraid of your plane wings snapping during turbulence? Well, yes, it's true, they can snap, but only in extreme cases that would never happen in the air. Before approval, planes undergo wing flex tests, where their wings are bent far beyond what they would experience during a storm. They're actually 150% stronger than they ever need to be, so next time you see your wings flexing, you can relax.
The case loads are results or are obtained of a simulation of conditions that an aircraft may confront, like on ground, on cruising, turbulence, lightning, or bird strike, landing phase. So we get the loading of each case load apart, and then we're gonna have in the next chapters. Probably we're gonna see more details about the static. I'm not sure about the fatigue. Maybe in another videos. But for these chapters, we're gonna talk especially about the static. We are in the end of this first chapter, and so by the end of this video I'm inviting you to leave any question or comment of the video below in the comments. Thank you for listening, thank you for your attention.